Good morning, everyone, and welcome to the Royal Swedish Academy of Sciences and this press conference. The Academy has concluded its meeting, and we are ready to announce this year's Nobel Prize in Physics. And as usual, we'll do it both in Swedish and in English. I'm Göran Hansen. I'm the Secretary General of the Academy. And to my right is Professor Nils Mårtensson, the acting chairman of the Nobel Committee for Physics. To my left, Professor Tors Hans Hansson, who is not a brother of mine, but a member of the committee and an expert in the field of the prize. Later on, we hope to have one of our new Nobel laureates with us on the phone. This year's Nobel Prize is about exotic matter in the quantum world. Årets Nobelpris handlar om exotisk materia i kvantvärlden. Kungliga Vetenskapsakademin har beslutat att utdela 2016 års Nobelpris i fysik med ena hälften till David J. Fowles och andra hälften till F. Duncan Haldane och J. Michael Kosterlitz för teoretiska upptäckter av topologiska fasövergångar och topologiska materiefaser. The Royal Swedish Academy of Sciences has decided to award the 2016 Nobel Prize in Physics with one half to David J. Fowles and the other half to F. Duncan Haldane and J. Michael Kosterlitz for theoretical discoveries of topological phase transitions and topological phases of matter. Für theoretische Entdeckungen topologischer Phasenübergänge und topologischer Materiephasen. Pour leur découverte théorique de transition de phase topologique et de phase topologique de la matière. За теоретические открытия топологических фазовых переходов и топологических фаз материи. You have our new Nobel laureates and the pictures on the screen above me. Some personal information. David J. Fowles was born in Bearston in the United Kingdom in 1934. He is now emeritus professor at the University of Washington in Seattle in the United States. Duncan Haldane was born in London in 1951. He is the Eugene Higgins Professor of Physics at Princeton University, New Jersey, United States. And J. Michael Kosterlitz was born in Aberdeen in the United Kingdom in 1942. And he's currently Harrison Farnsworth Professor of Physics at Brown University, Rhode Island, USA. So that's the announcement. And now Professor Nils Mårtensson, the acting chairman of the Nobel Committee, will provide some introductory remarks on the Nobel Prize in Physics. Nils, please.
Yeah, this year's Nobel Prize recognizes important discoveries in the field of condensed matter physics. And today's advanced technology, take for instance our computers, rely on our ability to understand and control the properties of the materials involved. And this year's Nobel laureates have in their theoretical work discovered a set of totally unexpected regularities in the behavior of matter, which can be described in terms of an established mathematical concept, namely that of topology. This has paved the way for designing new materials with novel properties, and there is great hope that this will be important for many future technologies.
Thank you, Nils. And now Professor Tors Hans Hansson will give us some insights into the discoveries that led to the Nobel Prize. Hans, please.
So I'm very happy to be here and to tell you about this very deep and actually very beautiful work that is at the basis for this year's prize. And I will start by explaining to you a concept from the citation that might not be familiar to you, and that's the concept of topology. So I brought my lunch, and here you see, it's a cinnamon bun. Here I have another thing. I have a bagel, okay? And here I have a pretzel. The Swedish pretzel with 2 holes in it. Now, for us, you know, these things are very different. This is sweet, this is perhaps salty, different shapes, etc. But if you are a topologist, it's only one thing that is really interesting with these things in which they differ. This thing has no hole. The bagel has 1 hole. The pretzel has 2 holes. The number of holes is what the topologist would call a topological invariant. And just as you cannot have a half a hole or 2 2/3 holes, you can, for a topological invariant, only have integer numbers, okay? Only integers. And another thing which is very important for the following with topological invariance is that it takes something to change the topological number. I take this thing, you see, I can bend it a little bit, compress it, but in order to make it to change number of holes, I have to do something drastic. I have to break it apart. And this stability of the topological invariance is going to be important. So what does this have to do with physics? Well, if we go back to 1980, it was a beautiful discovery made by Klaus von Klitzing. He gave him a Nobel Prize in 1985, actually, for what's called the quantum Hall effect. What he did was that he took electrons, he confined them into thin layer at very low temperature and at extremely high magnetic field. And what he found was very amazing. He found that when he measured the electric conductance in this system, he could see it came in steps. Nothing, or 1 unit, or 2 units. And this unit that he measured was to an extreme precision. Sort of unexpected, because in these experiments you cannot control temperature and all other things very carefully. So why could you get something which is so precise? There were ideas about that, but the real breakthrough came with the discovery of one of today's laureates, David Towers, who could show that these steps here actually can be explained as such a topological invariant. It's not exactly as the number of holes in a bagel or a pretzel, but it's something very, very similar. And this also explains why it is so precise, why it's so robust, why you get integer steps. And later on, 1988, Duncan Haldane, another of today's laureates, showed that you could do the same without having this very strong magnetic field. And for the continuation of this field, that was very, very important. Now, let's move on to the next concept in this citation, namely topological states of matter. Now, what is a state of matter? Well, this is something that you presumably know from school. If high temperature, you can have a gas. Lower the temperature, you get a liquid. Lower more, you get a solid. But when you lower temperature even more, close to absolute zero, there are new fascinating phases of matter. And the ones we talked about before, these electrons in a layer, that's such a topological phase of matter that you find at very low temperature. Now, this is not the only one. Haldane, in 1983, looked at another kind of system, a set of magnetic atoms in a chain, and he could show that even in this case you had such an exotic topological phase of matter. And now actually the race is on, and you look for topological phases of matter in chains, in layers, but also in ordinary three-dimensional materials. So that was two things. It was topology, it was states of matter. Now we come to the third, phase transitions. What's a phase transition? Well, How do you go from a gas to a liquid to a solid? You do it. You lower the temperature. Now, what is it that really happens? And this physicists have studied for a long time, and it was a good idea about how this transition occurs. And in particular, people believed that if you had these very thin layers, for instance, a thin liquid layer of helium, you would never have such a phase transition. That had been proven mathematically. But when people prove that something cannot happen, it might be that they haven't thought of everything. And the thing that they did not think of in this case was this thing. They did not think of, well, not tornadoes, but vortices. A tornado is like a big vortex. And it's topological in the sense you can have one tornado. If you're unlucky, you have two perhaps. But you cannot have half a tornado. It's topological in the same way as the number of holes. That's a big one. Here is a small one. This is the artists rendering some layers of liquid helium. And you see there are small vortices here. Here we have a blow up. You can see the liquid is whirling around here. Now, at very low temperature, these vortices always comes in pairs. Actually, it's one vortex going in this direction and the other one going in that direction. It's a pair of vortex and anti-vortex. They keep together. When you raise the temperature a little bit, then what happens is that these super tight pairs, now they will sail away and they become free. And that is a phase transition, a completely new kind of phase transition driven by topological effects. And this was also something that you could apply in many places, and the basic paper was written by Kosterlitz and Thouless, who found the phase transition and understood the vortex mechanism, and in a later paper by Michael Kosterlitz, he also worked out the detailed mathematical theory. And this is something that applies not only to helium films, but to lots of systems, and it's been very important for the following. Now, that was very shortly what it's about. Now, I will answer the question that you are going to ask, namely, what's it good for? Because I know you're going to ask that. But before I answer that question, let me tell you something that I feel deeply about, the committee feels deeply about, I think all people in physics feel deeply about. And that is that this prize here is for theoretical discoveries. It has combined beautiful mathematical and profound physics insights and achieved unexpected results that has been confirmed by experiments. That's what the prize is for. It's really beautiful and it's deep. Having said that, this work has inspired lots of activity in labs all over the world, international research. Scientists are hoping for practical applications in new electronics, new materials, even perhaps components in the future quantum computer. It has opened this field. It's very exciting, but the prize today is for this. Thank you.
Thank you, Hans. We may now have one of our new Nobel laureates with us on a phone line.
Hello.
Hello, Professor Haldane. Are you there?
Hello, yes, I'm here.
Thank you for...
And it was a very nice summary, yeah.
Thank you for being with us again. This is Göran Hansson, who called you about half an hour ago.
Yeah.
And I'm now sitting in the session hall of the Academy together with journalists from all over the world, and I'm sure they are eager to ask you some questions. So are you ready to take questions?
Yes, sir.
Who would like to start? Thomas von Heine? You got the microphone there.
Good morning, sir. Congratulations.
Thank you.
There is one very, very basic question, but it's easy to put it, the first one. What was your reaction when you had the phone call half an hour ago?
Well, I was... as everyone else is, I was very, very surprised and very gratified. I know this work has certainly led to a lot. That was a long time ago, but it's only now that the it's only now that a lot of tremendous new discoveries, which are based on this original work and have extended it in many ways, are now happening. And it's certainly a subject of great, a huge amount of work is going on the topological insulators, which were totally surprising phenomena, which grew out of this earlier work that David Paulus and I and Mike Koslitz had done. And there's great hopes for this work these new materials to have a big impact in things like possibility of topological quantum computation and lots of such things.
Thank you. More questions? Yes, please, lady over there.
Okay, congratulations.
Thank you.
A lot of this work was made in the 70s, for instance, and I wonder if we see any applications today on your work around us.
Yeah, well, my work was in the late 80s, and at the time it seemed very abstract, and I even wrote in my paper that the model I looked at was an interesting toy model, and it was of something which turned out to be quite like graphene is today. And at the time I felt it was of scientific interest and mathematical interest and very fascinating as a consequence of quantum mechanics that we hadn't guessed at. But I didn't think it would ever find a practical realization. But if something is actually possible, it'll eventually, with material science, any kind of unexpected possibilities will eventually lead to some concrete realizations. And these materials would have a possibility that information, either electronic or in other versions, light, can travel in one way around the edge of the system, and you can have without the possibility of of the information in the signal being disrupted by impurities or bends in the path. And so this aspect of things has got at least has a theoretical possibility of having great practical implications in these in subjects like the dream of building quantum computers. So what it's led to really is that it's taught us that quantum mechanics can behave far more strangely than we would have guessed, and we really haven't understood all the possibilities yet. And what these discoveries by myself and earlier by David Paulus and Mike Koslitz really show up of really that we have a long way to go to discover what's possible, and a lot of these things were things that one wouldn't initially have dreamed were possible, and it's gone on in recent years. In the last 10 years, these ideas have been extended, and it turned out that a lot of materials that people had looked at for many years did have these topological properties that had just never been seen because people hadn't looked for them. And when it was realized this was possible as a theoretical discovery, that you could extend my work to a broader class of systems that was by Charlie Kane and Jean Milly. Then they realized this could be extended to three-dimensional materials and just regular crystals and things. And now people are just looking, and you can find topological physics in many places now. And it was just something that's been completely overlooked, because it occurred on the surface of materials rather than in the whole material itself. And it's really I've been very surprised by all the recent unexpected discoveries and extensions of this, and suddenly people are realizing that the topological effects in quantum mechanics are just a tremendously rich subject. And
fantastic how a set of discoveries by small group of scientists can now explode in the whole research field.
Yeah.
Are there
Yeah.
more questions from the journalists here? Yes, Maria Gunther. We have one more coming up here.
Yeah.
Hello, my name is Maria Gunther from Dagens Nyheter. Congratulations to the prize.
Thank you.
I would like to know how you come up with the idea in the first place of this model.
Well, it really was trying to kind of crystallize, trying to come up with a clear, in fact, trying to show something else was wrong. Just to come up with a clear model to show that in principle, you could get this topological effect I was looking for, but really just the key point was to show that this effect that David Fowler had predicted, had found in the early 1980s in the context of very strong magnetic field, this quantum Hall effect could actually occur in a more general, just when you had some kind of magnetic materials that had broken time reversal invariance, but didn't require huge magnetic fields, and it was really just a toy model demonstration of something, and then I realized it was a very neat model. So I basically stumbled onto this, really playing with the mathematics of some model, and I think similarly David Fowler's discovery, he didn't really realize it was topological until he just found there was some number that was stable, and later on the mathematicians told us what the mathematical theorems and the topological classes that was this. So we basically, like most discoveries, you stumble onto them, and you just have to realize there's something very interesting there, and one never realizes the full implications of these things until other people have started thinking it's true and one realizes the big picture. So most of big discoveries are really that way. I think at least in theoretical things, you never kind of set out to discover something new. You stumble on it, and you have the luck to recognize what you found is something very interesting. And basically, the problem was that with all these things is that you really need to, if you don't really if you can't visualize what you're trying to do, if you don't really know what you can't. These things which are so surprising, it takes a while to do it, but to see it. But once you see it, you realize, why didn't anyone else think of that before? And really, one can't. The barrier to most of these things is that you just don't realize what's out there until someone stumbles over it. I think that's
okay. Thank you.
Yeah.
Are there more questions here from the journalists? Yes, the lady over there.
Congratulations on the prize. This is journalist from People's Daily from China. My question is, because I read the newspaper this morning, less and less people, especially young people, are less and less interested in physics. The first question is, what has inspired you to get research on the physics? And my second question is, what recommendation can you give to the nowadays young professionals? Thank you.
Well, I think my parents influenced me with a great interest in science, and I suppose the details of physics, like many things, is I had the great fortune to have a very inspiring teacher at Cambridge University, Phil Anderson, who is also later received the Nobel Prize, and I think partly the way he explained his unorthodox ideas and inspired me tremendously. And now I think actually this whole topological quantum physics has actually become an inspiration for a lot of a generation of young physicists in recent years, at least in condensed matter physics, and also it's now reaching a bit into particle physics, or people in in high energy physics have got interested. This whole possibilities of topological physics have actually been tremendously inspiring to many young people working in physics these days. And you see the coffee cup turning into the donut and back again as a meme in all kinds of talks. Yeah.
So let's hope that. I'm sure that you will be able to convey your enthusiasm to students and young scientists when you come here in December. So that was the last question. Thank you very much, Professor Haldane, for being with us at this press conference, and see you in December. Thank you. Bye-bye.
Thank you very much. See you soon. Bye.
Bye-bye. Are there any questions to the panel? Hans has promised to take maybe 1 or 2 questions before he has his lunch, and Nils and I are also available. I know that some of you are eager to move on because you have individual interviews and broadcasts and so on. If there aren't any further questions, then I think we'll close this part of the press conference and we'll proceed with individual interviews with Nobel Committee members for those of you who have requested such interviews. Thank you very much for your interest, and welcome back tomorrow for the Chemistry Prize. Thank you.
Professor Tors Hansson, you're a member of the Nobel Committee for Physics, and you just presented the Nobel Prize of this year. It is about exotic matter in the quantum world. So my first question would be, what is this exotic matter?
Well, exotic is not a precise scientific term. Exotic is something that expresses our wonder in front of something that is very unusual, very hard to understand. And I think also that has to be seen historically. What is exotic for us now might not be so exotic in 20 or 30 years. I guess, electricity was very exotic when it first came around. It's not so exotic any longer. But today, the basis of matter, I guess we come to that is at the basis of this year's prize is really exotic, yes.
And this matter, exotic matter, is also in the quantum world. So where is this quantum world?
Well, the quantum world is in a sense all around us. But quantum effects are not always very obvious to see. But when you cool down materials to very low temperature, then in many cases quantum effects becomes very much more visible, more apparent.
And then I have another exotic question perhaps. We have this bagel, and you had also a cinnamon roll. What do they do in this Nobel Prize context?
Well, they are actually there to illustrate something, and to illustrate that is not sufficient to just show the bagel. But I anticipated this question, so I brought also the bun. You see, when you have both the bun and you have the bagel, then you can see that the difference is that the bagel has a hole and the bun doesn't. And the important with the hole is that although things like taste or shape or deformation can change continuously, but the number of holes, which is something that we call the topological invariant, it can only change like integers. 1, 2, 3, 0. This has 0 holes, this has 1 hole. I challenge you to imagine what is a half a hole. What would be to have half a hole? You cannot have half a hole. You need 0, 1, 2. And this fact that you have integers that are of topological nature, that's intimately connected to the effects and the description of these phases that is at the basis of the prize.
And topology is kind of advanced mathematics and has a key role in this Nobel Prize of the year. What was the role of topology?
Well, the role of topology is, there are many roles of topology actually. One role of topology is that these so-called topological invariants, I took the example, the number of holes, actually directly gets into the mathematical description of these phases. Now, takes advanced mathematics to write a formula that counts the number of holes in a donut or calculates that there is 0 hole in a cinnamon bun. That's advanced mathematics, but to understand the concept that this is 1 hole, that is 0 hole, that anyone can understand. And that is actually the important thing for the basic result.
So what were the discoveries of this year's laureates?
It was theoretical discoveries that we should remember. And it also illustrates in a very nice way the interplay between physics and mathematics, where theoretical physics is in the actual at the crossroad. Because the quantum Hall effect, which was the starting point for David Fowler's understanding of it as a topological effect. There was an experiment that was already done, and he explained the experiment using these topological invariants. While in another case, the case of Duncan Haldane, who predicted certain properties of other topological states, actually chains of magnetic atoms, and also something similar to the quantum Hall effect but without a magnetic field. That was theoretical discoveries that predicted effects that was later seen in experiment. In one case, actually 25 years later, and it took much more advanced experimental techniques to do it.
Were there very surprising experiments, or did they expect that it will come?
In many cases, when you have a theoretical possibility, since there is so much variety in experiments you can do, in materials, in experimental setups, in many, many cases you come up with a case where it's actually realized. You cannot say for sure, but experience shows that that happens very often. So that's of course very exciting, you know.
So what are the possible applications of this exotic topological matter in the future?
I can just tell you what people are dreaming about, but also working very hard in the labs to do. And that is to get new materials which has, you know, interesting properties of conducting electricity, but also conducting other things like what is called spin. And the dream is that this can be used for carry information. It also has quantum mechanical properties, something that is called entanglement, that makes people hope that perhaps you can use these things to code quantum information in an efficient way. So who knows, you know, there might be a future quantum computer where topological effects are important. We don't know, but I certainly know people are speculating about this.
Can you tell us a little about the laureates? The prize is awarded half to David Towles and half to Duncan Haldane and Michael Kosterlitz. Can you explain this division?
Yeah. There are two parts in the citation: topological phases and topological phase transitions. That is how you go in between them. And David Towles has given important contributions to both of them. To topological phase transitions together with David Towles, and to topological phases, he did this important work, and there later Haldane did also very important work. So David Towles has a share in both these parts of the citation. That's why he gets 50%.
Thank you very much for taking your time. Thank you.
Thank you. Okay. Vad sa du?
Han knuffade på mig så jag förstod att vi får sluta. Var det så?